Salam and welcome everyone. So today we're going to be working on the question on the screen that says the molar volume of a certain solid is 142.0 centimeter cube per mole at 1.00 atmosphere and 427.15 Kelvin, which is its melting temperature. Then they also said the molar volume of the liquid at this temperature and pressure is 152.6 centimeter cube per mole. At 1.2 megapascal, the melting temperature changes to 429.26 Kelvin. Calculate the enthalpy and entropy of fusion of the solid. So the first thing you have to do when you have a question like this is for you to break down the information. So for the solution, we're going to read each bit of information from the question and then write out the parameters. So the molar volume of a certain solid. So for the solid, the molar volume is 142.0 centimeter cube per mole at 1.00 atmosphere. So the pressure is 1.00 atmosphere. And the temperature we were told is 427.15 Kelvin. So next, we're told that the molar volume of the liquid is one of the liquid at this temperature and pressure. So what this is saying is that the temperature and the pressure does not change. It's still 1.00 atmosphere um, and 427.15 Kelvin. So they basically what's going on here is going to be that the melting occurs from solid to liquid, and it's a reaction where basically it's a process that occurs in equilibrium where the temperature and the pressure still remains the same, and the only thing that changes is the molar volume. So this new molar volume for the liquid is 152.6 centimeter cube per mole. Then we're told at 1.2 megapascal, the melting temperature changes to 429.26 Kelvin. So what this is telling us is that we're going to have a new pressure, which we can call P star, 1.2 megapascal, which is also the same thing as 1.2 times 10 to the power of 6 Pascal, or 1.2 times 10 to the power of 6 Newton per meter squared. And the temperature changes to 429.26. So T star is 429.26 Kelvin. So calculate the enthalpy and entropy of fusion of the solid. So that's going to be the enthalpy of fusion, what is it? As well as the entropy of fusion, what is it? So yeah, that's basically it. We already know in physical chemistry, anytime we're given questions, one thing we can simply do is to look at all of our information and look at the type of formula that is going to befit the process. So we have a question where we're given molar volume, we're given initial molar volume, final molar volume as a result of melting. So for example, the initial molar volume will be the solid because it's a melting phase. So it's a melting process. So of course, the initial process will have the initial molar volume for solid, and then the final molar volume will be that of the liquid. So I want to just put that there because this information will be necessary when we start solving. So you may be wondering, how do we go about solving this? The first thing you have to note is that in your Physical Chemistry Atkins 11th edition textbook, there is something called the slope of liquid boundary, and that formula can be integrated to actually get the formula we're supposed to use to solve this question. So the formula we're going to use to solve this question is P is equal to P star plus change in enthalpy of fusion over T star times the change in molar volume of fusion multiplied by T minus T star. From this, we can see that we have P, regular P here, that's 1 atm. We have regular P, we have P star, which is 1.2 megapascal. We have T star, which is simply 429.26 Kelvin. And we also have regular T, which is 427.15 Kelvin. So the only things we don't have is a change in enthalpy of fusion, which is what we're supposed to solve for. And we were also not given um, the change in molar volume of fusion, or you can always call this change in molar volume of fusion. You can also call it the change in molar volume that accompanies melting. So you may be wondering, okay, how do we do this? Well, this is not hard because we've been given the initial molar volume before melting and the final molar volume of the liquid after melting. So that's how we're going to solve this. So we have The change in molar volume of fusion is going to be the final molar volume, so the one for the solid, okay, minus, sorry, that's the one for the liquid because it's a melting process. So the molar volume of the final molar volume, which is the one for the liquid after melting, minus the molar volume initial or the initial molar volume of the solid before melting. So we see V final is going to be 152.6 centimeter cube per mole. So 152.6 centimeter cube per mole minus the V initial, which is simply 142.0 centimeter cube per mole. So the change in molar volume of fusion, when you input this information in calculator, you end up getting 10.6 centimeter cube per mole. So this is basically this. So now that we have this information, we can now input all of our values in the actual formula in order for us to solve this question, which is solving for the enthalpy of fusion. But before we do just that, I want to quickly mention something. Even though we sometimes can find parameters easily in physical chemistry and we can just simply input different values into a formula to solve it, that is not really all that is necessary. You still need some level of brain power. So, for example, what I'm trying to say is we have centimeter cube per mole. Now, we were told to solve for the enthalpy of fusion, and we know that enthalpy is related to energy in some way. Basically, enthalpy is just heat energy at constant pressure or whatever you want to call it. But what I'm trying to say now, particularly, is the fact that enthalpy in of itself has joule per mole as its what do you call it, joule per mole as its unit. So whenever you're dealing with physical chemistry, you have to pay attention to the units. I know there was a point in time we were doing perfect gases or ideal gases where you could have atm, dm cube, then you could also have pascal meter cube or pascal dm cube. Now whenever we're dealing with enthalpy, the real units you're going to be dealing with all the time is going to be joules. And if you're dealing with joules, that means your pressure has to be meter cube. Sorry, that means your pressure has to be in pascals or Newton per meter squared. And your volume always has to be in meter cube. There is no centimeter cube anymore or decimeter cube anymore. And the reason is because joules is equal to Newton per meter squared. Sorry, joules is equal to Newton meter. And whenever we're doing calculation, we need to be able to cancel out our information so that when we're getting joules as the unit, we actually did all the units conversions correctly and end up with the correct answer. So what this is telling you right now is that this enthalpy, this change in molar volume of fusion of 10.6 centimeter cube per mole will need to be converted to meter cube per mole in order for us to successfully substitute into the equation. So we have 10.6 centimeter cube per mole times, doing dimension analysis, since we want meter cube per mole up top, we can just say meter cube, meter cube up top, and then centimeter cube down below. So how many centimeter cube is in 1 meter cube? We have 1 meter cube is equal to 1 million centimeter cube. So we cancel out centimeter cube, we cancel out centimeter cube. So 10.6 meter cube divided by 1 million mole would just end up giving you 10.6 times 10 to the power of -6 meter cube per mole, which is simply the change in molar volume of fusion. So yeah, that's it. Now you're like, yay, we have all the information, so we can simply substitute. So let's just simply rewrite the formula again before we continue the next part of the calculation. So we have E equal to P star plus change in enthalpy of fusion divided by T star, change in molar volume of fusion multiplied by T minus T star. So remember what we're actually looking for here is the change in enthalpy of fusion. Now I want to do something again. I'm not trying to stress anyone out, but I have to say this. Now we can see how complicated this formula is. while we can substitute everything, it's just going to make our work a lot more cumbersome. So one thing we can do is to rewrite this formula in terms of change in enthalpy of fusion. Yes, we're going to be doing some algebra. Anyways, so to do that, P is equal to P star. We can just simply just rewrite it as P minus P star is equal to changing enthalpy of fusion multiplied by open bracket T minus T star divided by T star, changing molar volume of fusion. So of course we're going to multiply, cross multiply. We end up with P minus P star, T star, change in molar volume of fusion is equal to change in enthalpy of fusion. Sorry, yes, enthalpy of fusion times T minus T star. So of course, in order for us to continue this, in order for us to have the formula in terms of changing enthalpy of fusion, we just divide both sides by T minus T star. So you cancel out this, you cancel out this. So the new formula is going to be change in enthalpy of fusion is equal to P minus P star times T star times change in enthalpy, times change in molar volume of fusion divided by T minus T star. So yeah, this is your new equation. Now we can comfortably substitute. So we know our pressure, regular pressure is 1 atm, 1 atm 2 Pascal. Remember I told you, because we're going to eventually get our final answer in joules, we have to change it to Pascal or Newton per meter squared. 1 atm is equal to 101,325 Pascal or 101,325 Newton per meter square. Since we're dealing with calculations now, I'm going to put everything in terms of Newton per meter squared. So that's going to be change in enthalpy of fusion is equal to 101,325 Newton per meter squared minus, what is P star? 1.2 times 10 to the power of negative 6 Newton per meter squared. We can also see that as 1,200,000 Newton per meter squared. Okay. Multiplied by, what is T star? T star is 429.26 Kelvin. Times change in molar volume of fusion, which we determined to be 10.6 times 10 to the power of negative 6 meter cube per mole, times 10.6 times 10 to the power of negative 6 meter cube per mole. All of this information divided by T minus T star. We know our temperature, regular temperature T, is 427.15 Kelvin. 427.15 Kelvin minus 429, which is a T star, 0.26 Kelvin. Now we work on using our calculator. So when we go ahead to do 101,325 minus 1.2 million, we end up with 109, we end up with 109,8675. So we end up with this value here, Newton per meter squared times 429.26 Kelvin times 10.6 times 10 to the power of negative 6 meter cube per mole. Sorry, let me rewrite this so that it's cleaner and there's no confusion for anyone. So you end up with 1098675 Newton per meter squared times 429.26 Kelvin times 10.6 times 10 raised to the power of negative 6 meter cube per mole divided by negative 2.11 Kelvin. I actually just realized I made a little error. Of course, 101,325 minus 1.2 is going to give you a negative number. Since 101,325 is actually less than 1.2 million. So I'm supposed to add a negative here, which I genuinely forgot to write, but thank God I caught it quick. Anyways, you have meter squared here, you have meter cubed here. We're going to cancel out meter squared, we're going to cancel out meter cube. What we have left is meter. We have Kelvin here, we have Kelvin here. We're going to cancel out the units for temperature. So what you end up with is negative in the numerator as well as negative in the denominator. So we cancel out the negative. Now we have a positive value. So we have change in enthalpy of fusion is now going to give you everything in the numerator, which is 4,974.5697 Newton meter, because we multiply the Newton here and the meter here. So Newton meter per mole divided by 2.11. So change in enthalpy of fusion is now going to be 4974.5697 divided by 2.11 would end up giving 2,357.62 joule per mole. And joule per mole is simply the same thing as Newton meter per mole. So that's basically what's going on here. So yeah, that's it. So now we've successfully gotten the change in enthalpy of fusion. But as chemists, we have to make sure we put our work in the proper number of sig figs and not necessarily the raw answer. So to do that, we have to go back to the question and see the lowest number of significant figures. So we see that the values we have 4 sig figs here, 3 sig figs here, 5 sig figs here, 4 sig figs here, 2 sig figs here, and 5 sig figs here. And we see that we end up putting our final answer in 2 sig figs, because that's the lowest number of significant figures. So anyways, so what that would look like now will be the change in enthalpy of fusion is simply going to be 2.4 kilojoule per mole. And I'm sticking to 2.4 kilojoule per mole because I decided to go from joule per mole to kilojoule per mole because that's how neat we can get our work. So of course, from joule to kilojoule is to divide by 1,000. So we end up with 2.4 kilojoule per mole as the change in enthalpy of fusion. Now that we have successfully done that, we see that we're still not done with the question. The question asks us to find the change in entropy or entropy of fusion. So the entropy of fusion is the next thing on our list. So entropy of fusion. So basically, what are we supposed to do with this? To understand how we can solve for the change in entropy of fusion, we now have to remember what we've done in the previous chapter of the Atkins Physical Chemistry 11th edition textbook, which is this formula right here, which is just basically the transition, how to find the change in transition entropy. So this is basically the formula I'm supposed to use. And I'm going to talk about it a little bit in detail. So this formula right here is called the entropy of phase transition, where we have in this place the enthalpy of phase transition, and we have this one which is called the normal transition temperature. So you can see, right? You can basically see what all of this thing is. You have the enthalpy of phase transition and the normal transition temperature, and that's basically it. So you can be wondering now, okay, I'm beginning to make sense of this. We have our enthalpy of fusion. So what else are we supposed to do? Well, since we have the enthalpy of fusion, you're not going to be wondering how do we now determine the normal transition temperature? Because when we go back to our question, what you're going to realize is simply that we have a temperature of 427.15 Kelvin, as well as a temperature of 429.26 Kelvin. And you're going to be wondering which one of them do we have to use, because we can only have one normal transition temperature. Well, to do this is very, very simple. we have to know that the normal transition temperature is defined as the temperature at which two phases are in equilibrium at 180 m. So transition temperature is the temperature at which two phases are in equilibrium at 180 m. So when we go back to our question, we will see this. We see that we're told the molar volume of a certain solid is 142 blah 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 at 180 m, okay, and 427.15 Kelvin. It's melting temperature. Then we also told the molar volume of the liquid at this temperature and pressure is 152. Now we see that the temperature and pressure remains the same during the process of melting. The only thing that changes is the molar volume. And the temperature there is at 180 m. So that means at this particular pressure, we have a temperature of 427.15 because our solid and our liquid are currently at equilibrium. So the phases are in equilibrium with one another. So basically, that's it. That is basically it. Anyways, so we now know that our enthalpy of fusion is going to be 2357.62 joule per mole. And then the transition temperature is going to be 427.15 Kelvin. Yeah, so that's basically this information right here. So now we can simply substitute. And now you may be wondering, well, why didn't we use 2.4 kilojoule per mole? We don't do that in science. You always use the raw value, and then at the end of your calculation, then you can do what's it called? You can do an approximation. So that's how work is done. Anyways, so we're going to use the raw value. So the change in entropy of fusion becomes 2357.62 joule per mole divided by 427.15 Kelvin. So of course, we input this information in our calculator to end up getting 5.5194 joule per mole. And again, we are scientists. We're not going to leave our answer just like that. We have to actually put it in the proper number of significant figures. So the change in entropy of fusion is going to be plus 5.5 joule per mole. So this is basically the answer to this question. If you have any questions, please, please, please ask me in the comment section of this video. If you have any suggestions or concerns, also put in the comment section. And for those of you who would like me to tutor you, I'm a tutor who helps students succeed in all their STEM related courses, whether they're in middle school, high school, and college. If you would like to make use of my tutoring services, make sure you email me at shahabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.